So, today I am going to take the next unit process for pyrometallurgical extraction of metals from ores. So, the next process is smelting. Now, in fact, let us see what is smelting. What is smelting? Now, mind you, there is a difference between melting and smelting. In the smelting, the definition what I am going to give now. Melting means you are melting, for example, pure metal or alloy or whatever. So, that is a melting, but smelting is a different. So, there is a difference between smelting and melting. The smelting is, what is smelting? It is a unit process. It is a unit process to heat a mixture of ore concentrate plus flux plus fuel if necessary. Above the melting point, now this above the melting point is different than what was in the roasting. In the roasting, we were carrying out the process below the melting point, so that the initial state of the raw material was solid and final state is also solid. But in case of smelting, the initial state of the raw material is solid, but the final state is the liquid and gases. So, that is a very important difference between the two. So, above the melting point, to separate the gangue mineral from ore in the liquid state. This is a general definition of smelting. The whole objective is to separate the gangue mineral, but remember the state of the gangue mineral in case of smelting is the liquid. It is a difference between roasting and smelting. Again, I will like to point out, in the roasting both states initial and final were solid, but in case of smelting initial state is solid and the final state is that of liquid. Now, when metal is separated as sulphide, from smelting of ore, then we called met smelting. So, in fact, in met smelting we have ore concentrate plus flux plus air plus fuel if necessary, then we have met, slag and gases. And the typical example of application of this met smelting technology in case of copper extraction. Rather, in case of extraction of copper from sulphide, sometimes nickel from sulphide, and sometimes antimony, Now, another say, when metal is separated, as liquid then it is called reduction smelting. Then it is called reduction smelting. So, that means we have matte smelting and we have reduction smelting. In matte smelting, we separate gangue mineral and produce a matte. In reduction smelting, we also separate gangue mineral, but mind you, here we produce liquid metal. Now, some examples of reduction smelting. Some examples of reduction smelting, the famous example all of you know is the production of pig iron from iron ore concentrate is one such example. Another example is zinc from zinc concentrate. Now, here slightly there is a way, because here zinc is produced in the form of vapor and then they are condensed and ultimately you get the liquid. Another example of reduction smelting is lead from lead ore concentrate. So, each one we will take in detail, we will go, we will solve the material and heat balance and so on. So, first I will be concentrating on matte smelting. Matte smelting. Now, obviously, there are certain advantages of extraction of metal through matte smelting route, because what we are doing in matte smelting, we are separating gangue mineral and producing a matte from the copper ore concentrate. Now, what are the advantages of it? The advantages of matte smelting. First of all, low melting point of matte. Low melting point of matte. Now, for example, Cu2s plus FeS, it has around 1000 degree Celsius is its melting point. So, that means you do not require a very high amount of energy to produce the matte. This is the one such advantage. That means you will require less amount of thermal energy by converting the metal of the ore in the form of sulphite and then to extract the metal. However, it will vary from reserve to reserve or metal to metal, particularly for sulphide ore, where direct reduction of sulphide to metal is rather relatively difficult. In some cases, the matte smelting route is technologically feasible and also energy efficient. You are seeing, for example, in copper extraction, the matte which consists of Cu2s and FeS, it has a melting point of around 1000 degrees Celsius. Also, another advantage is that the Cu2s which is contained in the matte, it does not require any reducing agent. That means, Cu2s of the matte, it does not require any reducing agent in the sense of say carbon or those reducing agent, they are not required. It is say by blowing oxygen you convert to oxide and then it is a sulphide oxide reaction that lead to the production of copper. So, that is the another advantage of having the matte smelting. This is for example, for copper. Similarly, if we take the nickel mattes, this is for the copper mattes. Similarly, nickel mattes, say nickel mattes, they are typically contain FeS plus Ni3S2 plus Cu2s. This is typically the nickel matte. Now, here the melting point of Ni3S2, melting point of Ni3S2 is around 800 degrees Celsius. whereas Ni3S2 plus Cu2S, it forms eutectic. If you see the phase diagram, forms eutectic at 720 degrees Celsius and 85% Ni3S2. So, what is said, I mean what I wanted to tell you is that the MET smelting technology is sometimes suitable for extraction of metal from sulphide ore, particularly when sulphide ore is associated with iron also. And for your information, most of the sulphide ore, they are associated with iron. So, in that case this MET smelting technology, well, for sulphide ore is good, and because of the advantages. Now, what is again MET smelting? So, if I want to represent in the form of the reaction, I will put it, say copper ore concentrate plus flux plus air plus fuel if necessary, then of course plus heat externally if it is sufficient, otherwise you have to supply it by combustion of the fuel. That will give you MET plus slag plus gases. Now, this is what I am referring now to MET smelting of copper ore. I am referring now to MET smelting of copper ore. That is what the subject matter of the following lecture. Now, well, here what is a MET? Already I have said what is a MET. In connection with the copper melting, say MET is a molten mixture, essentially of Cu2S plus FES. It sometimes it may contain oxygen, and say in the form of Fe3O4. I am talking the industrial MET. It is very difficult to control the dissolution of oxygen in the MET during the smelting stage. So, sometimes you may get industrial MET may consist of Cu2S plus FES plus Fe3O4, but in the problems which you will solve, unless otherwise it is given, you will be considering MET is a molten mixture of Cu2S plus FES. If it had something, then it will be given in the problem, but for your information, the industrial METs may contain Cu2S, FES is there, but in addition to, because of the dissolved oxygen, it may form to Fe3O4 also. Now, say important thing in case of MET is to define the grade of the MET. MET grade, or you can also call copper grade of MET. You can call grade of MET, or sometimes you can also call copper grade of MET. Well, it is useless to call iron grade of the MET, because you are not concerned with the iron. So, that is why you call a copper grade, that means how much amount of copper is over there. So, this is defined a copper grade, or you say MET grade, you say the you are producing a MET of 40%, a 40% MET. That means it is having its copper grade is 40%. So, MET is always given in terms of copper, because it is used to produce copper, not iron. So, remember. So, the problem may have 40% MET, or the grade of MET is 40%, or copper grade of the MET is 40%, all have the same meaning. So, for example, if you write copper grade, it can be defined as amount of copper in matte, amount of copper in matte upon amount of Cu2s plus amount of FeS. Now, this is copper grade when matte is a mixture of Cu2s and plus FeS only. If it has Fe3O4 also, then amount of copper in the matte upon amount of Cu2s plus amount of FeS plus amount of Fe3O4 into 100. That is how you will define the density of matte. It is given in percent. Now, another important feature, the density of matte. Density of matte, that is equal to 5 to 5.5 gram per centimeter cube, and the melting point, it depends on say proportions of Cu2s plus FeS, but normally of the industrial grade matte, the melting point is between 1150 to 1200 degrees Celsius. So, you can imagine this matte smelting is usually carried out anywhere between 1200 to 1250 or 1300 degrees Celsius, not higher than this temperature. This is the what is a matte. Now, another product is slag. What is a slag now? What is a slag? Slag, remember, is a molten mixture, I am talking in connection with the copper smelting, is a molten mixture of mainly oxides. It may contain sulphide, it depends, but mainly it is a mixture of oxides. Say in smelting of copper ore concentrates, for example, in smelting of copper ore concentrate, the slag may contain SiO2, Al2O3, calcium oxide, FeO, Fe2O3, Fe3O4, and it may contain sometimes unreacted sulphide. Well, that depends on the process of smelting, but in ideal condition it will contain SiO2, all oxides are there, but some unreacted sulphide is there, well, it will also be there. Now, some of the properties which is required, some of the properties which are required for a slag, because slag is normally highly viscous. So, at the end of the process you have to drain out the slag as well as metal. So, some of the desirable properties are: 1, low viscosity, second, the solubility is important. That means, slag should be able to dissolve the oxides which are being separated during smelting of ore concentrate. That is an important thing, that is, you have to make a slag of composition such, so that the oxides present in the ore concentrate, they are dissolved, you have to form the liquid. It is a homogeneous liquid solution, rather molten solution. Third important property, it should have a low melting point. Should have a low melting point, because you will not go more than 1200 or 1300 degrees Celsius. So, at that particular temperature, the oxides which are being separated from the ore concentrate, they should be able to dissolve and they should be liquid. Now, here you should also think that slag normally here does not act as a refining agent in contrast to the iron making. So, that part we separate at the moment here. So, in case of this melt smelting copper slag, these are the say important properties that the slag should possess. Now, next let us consider some of the chemical reactions which can occur. The chemical reactions, for example, 6 CuO plus 4 FeS, 3 Cu2S plus 4 FeS plus SO2, or 2 CuSO4 plus 2 FeS. Now, the CuSO4 may form during roasting, you might have roasted at a little higher PO2 pressure. So, CuSO4 might form. So, this also has to reduce to Cu2S, because you have to reduce, otherwise you will be losing copper here. You have Cu2S plus 2 FeO plus 3 SO2. Now, here this should be FeO. Then you have Cu2O plus FeS, that is equal to Cu2S plus FeO. Now, that is what some of the reactions. Now, sometimes say oxygen has greater affinity, say oxygen has greater affinity for iron, has greater affinity for iron than copper. So, the unreduced FeS, it may react with Fe2O3 or Fe3O4. So, accordingly 10 Fe2O3, it may reduce with FeS, that may form 7 Fe3O4 plus SO2, or 3 Fe3O4 may react with FeS and it forms 10 FeO plus SO2. So, FeO and Fe3O4, FeO and Fe3O4, they are dissolved in the slag. Mind you, Fe3O4 is difficult to dissolve as compared to FeO. Density of slag, that is equal to 2.8 to 3 gram per centimeter cube. So, you are seeing there is a difference in density of matte and slag, and by virtue of this difference in density, we are able to separate say matte and slag. So, you have this is sort of interface. So, somewhere here you have the matte and somewhere here you have the slag. So, you can see now the matte smelting is able to separate the metal in the form of sulphide from rest of the ore. So, this matte it only contains in ideal condition Cu2S plus FeS and nothing else, plus little amount of Fe3O4 if oxygen has been dissolved, but normally it has Cu2S plus FeS. So, all impurities are eliminated, and here you have the slag may contain all SiO2, Al2O3 and plus all other impurities which you have in the ore concentrate. So, that is what this matte smelting process is. So, now it should also be remembered that higher oxides of iron are difficult to slag. I mean in general, higher oxides of iron, are difficult to slag, Slag means it is difficult to remove. This precaution must be taken during roasting. During roasting, you have to see that the iron should not be converted to Fe2O3 or Fe3O4. It will have a lot of problems in the smelting and further stages. So, therefore, a controlled amount of roasting is needed. Well, that is what the thing you should know. Now, say conventionally the technology of smelting Now, before I say about the technology smelting, the third component that was coming was the gases, right. The gases were also forming. So, gases essentially consist of SO2, normally sometimes SO3 may be there, but it depends on the oxygen content. So, SO2, nitrogen, if excess amount of air is used, then you have oxygen also, and sometimes SO3 could be there, well, depends upon the technology or depend on the process, depend upon the reaction and so on and so forth. These are the mainly the gases which you will find in the smelting. Now, if fuel is used, then you may get CO oblique CO2 depend upon the state of combustion. So, these are the gases. Now, conventionally the roasting is carried out conventionally smelting is carried out in reverberatory furnaces. In reverberatory furnaces fired with coal or oil. They are very long furnaces, and traditionally the smelting of copper ore is carried out in reverberatory furnaces. Still the reverberatory furnaces are used, but now these reverberatory furnaces are replaced in recent years by so called flash smelting. Flash smelting. Now, the advantages of flash smelting is that it combines roasting and smelting both, whereas in the reverberatory furnace the ore has to be roasted first and then it is transferred to reverberatory furnace for smelting purposes. Then a new technology came, that is the flash smelting. Now, here roasting and smelting both are combined. Now, the reason for this, you must have seen in case of roasting a large amount of sulfur dioxide is created. Now, this byproduct sulfur dioxide, it can be very easily used to form sulfuric acid, and there is very substantial amount of SO2 is being produced. So, now imagine you have at one stage roasting, take the roast product and then smelt it. So, you have SO2 in the roasting stage, then you have SO2 in the smelting stage. So, both you have to collect and then send it for the H2SO4 plant. This is little bit uneconomical as compared to a process which can do both these functions simultaneously. That means, you start with the ore concentrate and get a product which is liquid matte, liquid slag and gases. What will be the advantage of this? Here you will get a concentrated amount of SO2 only from one reactor, in contrast to a technology which has roasting first followed by smelting as it was done in reverberatory furnaces. So, the advantage of flash smelting is that you have ore concentrate, mind you, it is not roast ore, it is ore concentrate which is coming from the mineral beneficiation plant. Now, this ore concentrate plus fuel plus heat plus flux, you get here liquid matte plus slag, of course, liquid slag and plus gases. So, here the main interest in sulphide ore is in the SO2, sulfur dioxide. Sulfur dioxide and some proportion of sulfur trioxide is also formed, but the main reason for the development of this technology called flash smelting, which combine both of them together, is to see that how SO2 can be produced in a concentrated way, so that a large amount of byproduct can be converted into a sellable product like for example, H2SO4. So, in most of the copper extraction plant, the reverberatory furnace is being replaced by the modern technology which is called flash smelting. So, now in flash smelting what is being done? just a brief. In flash smelting, what is being done is that a mixture of dry concentrate, a mixture of dry concentrate plus flux together with oxygen or hot air is injected into a reactor. Now, remember, if you are exposed, and I think you are exposed to the course of kinetics, now you are injecting a very fine particles of ore concentrates. So, the reaction will be extremely rapid and very high temperatures are created in the flash smelting. So, accordingly control of temperatures is required. Now, this is a well developed technology. So, what I wanted to say that because of the reaction rate is very fast in case of flash smelting. So, here heat generated is sufficient, to carry out the smelting. Now, this flash smelting could be so called autogenous in nature also, where you may not be requiring any heat from the outside. So, this is what about the brief idea of what is smelting, and I hope with this brief introduction on smelting or on the matte smelting, we are able to solve the problems concerning material and heat balance in matte smelting. So, I will suggest that for further details, you may consult the reference, for example, H.S. Ray, R. Sridhar and K.P. Ibrahim, extraction of non-ferrous metals, You can also see a book which is, say, Rosenquist, Principles of Extractive Metallurgy. Plus, you can also see by Butts metallurgical problems. So, this is about the so called brief introduction, and to prepare you for carrying out the material and heat balance in the matte smelting. Now, what I have planned, let me go for a very simple problem and then we will go for the further problem. So, as such, first I will say, let us take it, say, in a copper ore, say chalcopyrite is 34%, pyrite 30% and SiO2 36%. Now, it is very simple, determine percent copper, percent iron and percent sulfur. Now, here you have to take, say, atomic weights of copper 64, iron 56, sulfur 32. So, it is a straightforward, you can find out percent copper, that will be equal to 34 upon 184 into 64. Well, by the way, chalcopyrite is, I will tell you what chalcopyrite is, that is equal to 11.83%. So, by the way, chalcopyrite, it represents a mineral which is CuFeS2. I think you know, because in several lectures I have said. Now, similarly, say percent iron, pyrite is FeS2. I write now pyrite is FeS2, that means pyrite, let us put FeS2. So, percent iron is coming from two sources, 34 upon 184 into 56 plus 30 upon 120 into 56. I hope you can add both of them, and that will be 24.35%. This is the percent iron. Now, similarly, percentage of sulfur, that will be equal to 34 upon 184 into 64 plus 30 upon 120 into 64, that will be equal to 27.83%. That is why the answers for this. Now, this just starting with the very easy, so that you can also solve the problem. So, let us see the next problem. So, next problem is second, say calculate percent gangue in chalcocite ore when copper is 11.83%. Do you know what is chalcocite ore? Chalcocite ore is a sulphide ore which contains Cu2s. So, chalcocite ore that is equal to Cu2s plus gangue. So, 11.83% copper is given. So, the gangue would be 100 minus 160 upon 128. So, next is say what percent of iron, in a concentrate of composition given say CuFeS2 34%, FeS2 30% and SiO2 36% is to be removed to make 40% matte. Now, as I said in the lecture, when I said to make 40% matte, that means what? That means the copper grade of the matte is 40% and rest nothing is defined, except when we say 40% matte, that means the only means of this, it has the copper grade of the matte is 40%, that is what I have to say. So, now let us put it in the solution. Say we put the definition, that will be 40 upon 100, that is the matte grade, that is equal to 11.83% is copper upon to have 14.78% plus percent FES. So, now if I solve this thing, then I will be getting 0.4 into 14.78 plus percent FES, that will be equal to 11.83. So, from here I get percent FES, that will be 14.795. So, percent iron, that will be 9.415. Now, this percent iron or this percent FES should remain in the mat. Now, what has to be removed? So, percentage iron to be removed, percent iron to be removed, that will be equal to total is 24.35 minus 9.415, that will be 14.935%. That means, I have to remove 14.935% of iron in a mixture which has been given CuFeS to this, FeS to this, SiO to this, if I want to get a met of 40% grade. Now, another problem, let us take it. You recall the problem 1. Now, the problem 1, the data refers to problem 1. So, if the ore concentrate of 1 if the ore concentrate of problem 1, let us put it, problem 1 is fused down, and only excess sulfur is removed, excess sulfur is eliminated, the question is what would be the composition of the resulting mat, Now, could you understand what does this mean? That is, you have to remove the excess sulfur from the ore concentrate of composition given in 1. So, what was given over there? It was given that CuFeS2 34%, FeS2 30% and SiO2 36%. So, the FeS2 it decomposes to FeS plus S. So, that is the excess sulfur that you have to remove it in order to calculate the met. So, percent Cu2S, that will be 14.78% and percent FeS, if you calculate, that will come out to be 38.25%. Then met grade that will be equal to, as defined, percentage copper upon percent Cu2S plus percent FeS into 100. If you substitute, that will come 22.2%. So, that is how you will be calculating the so called this particular problem. Now, another interesting problem is said, let us consider now a copper met may be represented by MCU2S dot NFES with no fixed values of M and N, with no fixed values of M and N. If the met grade is 38%, if the met grade is 38%, what would be the entire composition of MET? Right. So, this is a very simple. So, you have to again write down say 0.38, that will be equal to amount of copper upon amount of Cu2S plus amount of FES. So, all that now we have to put it. So, that will be equal to 128 m upon 160 m plus 88 n. Now, here again CuS molecular weight, atomic weight, all everything I have given. So, all that you have to solve. So, if you solve this equation, you will be getting, for example, 60.8 m plus 33.44 n, that will be equal to 128 m. Now, here all that you can calculate the ratio of m is to n, that is equal to 33.44 upon 67.2, that is equal to 0.5. So, that means you have the composition Cu2S into 2FeS. So, that is what the composition of MET is. However, in the ratio of m into n, say for example, 2 Cu2S 4 FeS or 4 Cu2S 8 F, whatever the composition, in all the composition range where the ratio of m by n is 0.5, the grade of MET will be 0.38.